All right, guys, let's get started. Just some housekeeping stuff. Keep an eye on Canvas. Get all your assignments done. Exam on Friday. It's going to be in person. If for some reason you have to quarantine, please reschedule with me. What else? If you're taking it at the testing center, make sure to schedule as well. They need to know you're going to be there ahead of time. They should have the exam, but I'm also going to touch base with them today and just make sure they have everything they need. We're not going to do a Scantron, so all you're going to do is circle the questions in the packet. I'm going to grade it over the weekend. You're going to have that grade immediately rather than wait for the scanning office to take care of everything. So you'll get your grades back a lot quicker that way. I think that'll be better for everyone. All right, so today and tomorrow, we're going to be talking about climate change. Specifically, we're going to break it down into 4 parts. We're going to talk about different things that happen on Earth that force the climate to change and affect and impact the climate. We're going to talk about Earth's past and how climate has looked like in the past parts of Earth's history and how that's affected life on Earth. We're going to look at the data that we see today, and we're going to discuss how Earth is changing now, and then hopefully we are going to break it down into what we can do about it. Keep in mind, this is a really complex topic. There is a lot of moving parts in climate change, and that's why it's such a hard thing to talk about in the public sphere, mainly because scientists are not good at breaking things down into digestible news snippets. So something as complex and huge as climate change, it's really easy to get lost in the mix and fall down a rabbit hole of misinformation and confusion. So that's why we're going to break it down over the next 2 days and try to make things a lot easier to understand. So this is a global model of the Earth that we're looking at right here. So if you look closely, I know it's still hard to see, but all of those moving parts are wind currents. And this is on a particulate map. So we're talking about particulates, that's small solid material that's brought up into the air. So if we're looking around at this, we're noticing not a lot of particulate matter brought up in the United States, not a lot in South America, maybe a little bit in, is that Paraguay or Uruguay? Does anyone know off the top of their head? I get the two mixed up constantly because they're like right next to each other. I think that's Paraguay, but I might be mistaken. But if we look over here, we got a lot of particulates coming out of this area of Africa and flowing over the Atlantic Ocean. You can see it's following all of these wind currents that we see moving across the surface of the Earth. So what's this big feature in the middle of Northern Africa? The Sahara Desert. So all that sand, all that fine-grained material, and all those crosswinds, they're going to get picked up with those crosswinds, going to be brought over. So we get sediment influx all the way from Africa. In certain cases, we can get it all the way from the Arabian Peninsula. We can get it up from the Himalayas. As you can imagine, if you're at a higher altitude, it's a lot easier to carry stuff up into the stratosphere. Also in this area up here, this is the Gobi Desert, another really high, really dry desert that picks up a lot of sediment and transports it through the air. Also, if you'll notice, it's kind of hard to see on this one, but we've got a lot of particulates near industrial centers as well, and that'll be important whenever we're discussing climate change. So let's change the legend here. Let's look at some other stuff. So let's do currents. We're going to do currents, and we're going to overlay the particulate matter, ocean mode. Let's just do straight sea surface temperature. All right, so this is going to be really important. Now let's make sure the right overlay is on. So that's waves, this is going to be currents. Okay. So the colors are showing different ranges in sea surface temperature. So as you can imagine, this big line right in the middle, that's the equator. Obviously at the equator, we're going to have most tropical environments, the warmest stuff, the warmest temperatures. But as we can see, all these currents are moving from different zones of temperature. So we've got these colder waters down here in the south near Antarctica. Those sea currents are going to bring up all of that cold water, and that's going to influence, we can see this like plume of colder water coming up along the coast of South America. That's going to continue up, and that's going to help us with a lot of our precipitation cells. So we end up getting cold water currents all the way from Antarctica that go all the way up into North America. So this is part of the problem with addressing climate change and talking about and discussing climate change. Everything on Earth is interacting as one big system. And we're going to try to break that system down into more manageable parts here in what we're going to do today. All right, let's go to the presentation. Okay. Let's make sure this works. Sorry for the multimedia extravaganza we got going on here. Okay, this is working. Okay, so we talked about balances and budgets before whenever we were talking about flooding, where we have influx of water and outflux of water, where we have precipitation incoming, and then we have runoff minus infiltration and interception and evapotranspiration. So we can create all these really simple equations to break down big concepts. So obviously we get solar radiation from the sun on our planet. So our radiative balance is the solar energy absorbed that we get directly from the sun. And then after we absorb it, we're going to lose some of it, energy lost to the surroundings, which is going to be, in our case, space. We're looking at the whole planet. So if we look at our solar budget and our energy budget, 48% of everything that comes in from the sun makes it to the Earth's surface. 23% of it is absorbed by the atmosphere, and then another 29% is reflected by the atmosphere. The atmosphere is really good at reflecting a lot of that solar radiation. If we got too much of that solar radiation, we would die. Our bodies are only able to handle certain amounts of solar radiation. As with any type of radiation, best case scenario is in small doses, as you can imagine. So because we are a sphere, all of our solar radiation isn't distributed evenly. So at those high polar altitudes, where latitudes, excuse me, where we have that big curvature of the Earth, that's going to reflect a lot more of that incoming radiation. Whereas on the equator, we're coming in at a straight line, almost perpendicular. So we're going to increase all of that radiation that we receive. We're going to have warmer average temperatures overall, where we have that direct sunlight. As we increase that angle, we're going to increase the reflection of solar radiation. So as we increase in our latitude away from the equator, we're going to decrease our overall temperature. So that's why the colder zones are at the poles. A lot more reflection. Because there's a lot more reflection, there's going to be a lot less heat available. But we're also broken down into different currents based on the oceans. The oceans are huge bodies of water that really control temperature regulation on the planet's surface. So this is going to help us distribute precipitation to different areas. So in that model that we saw earlier, we saw some of these colder currents coming up from Antarctica. So you can see in this picture, we have this cell of cold water basically surrounding South America. And because of that, cool waters, they don't release as much moisture as warm waters. They don't evaporate as readily just because they're not hot enough to evaporate. So if you don't have evaporation, you do not have water vapor up in the atmosphere, and you can't rain that down somewhere. So that's why we have the Atacama Desert high up in Chile, one of the driest places on Earth. In fact, we do some field research there, and there's 3 researchers, including myself there. We are the smallest organisms for probably 500 kilometers. That's how dry it is in the Atacama Desert. But because of this, we have all of this cold water coming up, and when it's interacting with the warmer waters of the equator, it's going to start to create these cells of circulating water. We get the same thing in the Atlantic Ocean as well. We're bringing cool water up past Africa. That's why we have the Namibian desert. And we're also interacting with these warmer waters around the east coast of South America. So we're creating these cells of warm water and cold water interactions. And this is what that looks like overall. So this is what's called a thermohaline, and it works a lot like a conveyor belt. If you were a drop of water in one of these areas, you would follow along that entire length of the conveyor belt and eventually come back to where you used to be. So these waters will circulate all over the surface of the Earth and then come back to their original position and then start this process all over again. So for our thermohalines, we've got warm water circulating up around Africa, crossing the Atlantic, coming into the Caribbean. We're bring those warm waters up past the British Isles. The reason the British Isles are so rainy for so long during the year, that's because we have all that warm water coming up from the Caribbean, going past the British Isles. Warm water carries a lot more moisture. You're going to get more evaporation, more precipitation. So after that, it's going to take a hard left, mix in with the stuff in the Arctic. We're going to get a lot of deeper waters up here. So we're going to mix in with some cold waters, and then we're going to bring those cold waters down the east coast of America. So that's why we don't, on the east coast, we're still a pretty humid area. We get a lot of rain, but not as much as the British Isles. So we get a lot less rain, a lot more temperate climate because we have that interaction with that cold water from those deep water currents. So, and that's going to go all the way back down into Antarctica. Okay, so a key component that we need to talk about is the difference between weather and climate. There are a lot of people out there that confuse the two. Climate is the average conditions over long periods of time, whereas weather is the daily stuff that happens at local sites on a daily situation. So today in Newark, we can say, oh, it's 22 degrees today. Is it 22 degrees in Newark every single day of the year? No, of course not, because we have seasonal difference. But we have an average temperature range that Newark has throughout the year. So that's more towards the climate. Climate is the long-term change. Weather is the daily stuff. So weather has high variability. Climate has more long-term averages. We need a lot more data and a lot more studying to understand long-term changes in climate than we do with weather. The best example I can do is imagine you're walking your dog down Main Street and you're going just from one end of Main Street to the other. And your dog is going all over the place. He's sniffing trees, he's going up to strangers, he's all over the place, and you're just walking in a straight line. So while your dog is making all these variations in the path, it's still staying on the same rough path that you were going. You're going from one end of Main Street to the other in a straight line. So even though there's all that variability in your dog's path, it's still following the same trend overall. And that's how we compare weather to climate. Weather is going to be a function of climate over long periods of time, but weather's a lot higher in its variability. So whenever we talk about things that change climate, we're going to be talking about climate forcings, things that influence that radiative balance, that influence how much solar radiation we're keeping, how much we're reflecting, and so on and so forth. So we can influence these things on long time scales, geologic time scales. So plate tectonics is a big one. Others on really, really short time scales. So volcanic eruptions, those big, flashy, violent events can also do those. Earthquakes, not so much, but volcanic eruptions, mass extinctions, real instantaneous short stuff. That'll change it. So here we're going to use those terms positive and negative again. Positive promotes energy absorption. So we're getting an increase in energy, positive, and or we're reducing energy loss. So if we're just retaining more energy, that's going to be a positive forcing. Negative forcing, we're getting rid of energy. We're promoting energy loss, or we're reducing the amount that we can absorb. So less energy, negative, more energy, positive. Okay, so the cryosphere is going to play a really important role. This is the sphere that I study a lot. So it's all of the water on Earth that's frozen in ice year-round, constantly. It's not really the precipitation that falls as snow. It's more the stuff that's locked up. We're talking about icebergs, ice sheets like in Greenland, glaciers that we have all over the mountainous areas in the world, ice caps on the poles, and of course permafrost too. That's a really important one that gets lost in the mix. Permafrost is just that water that's trapped in soil that's frozen year-round. That's going to be a really important one as well. So 10% of the Earth is covered in ice today. As we increase the amount of ice, as you can imagine, since ice is white, it's very reflective. Anytime you're outside in the sun and you're wearing like white clothing or reflective clothing, you're a lot cooler because you're not absorbing all of that solar energy. If you're wearing like a dark colored shirt or dark colored clothing, you're going to absorb more energy, absorb more radiation, you're going to feel a lot hotter. So the amount of ice that we have on Earth helps to reflect some of that solar radiation. So this is going to be a negative forcing. We're reflecting, we're not retaining any energy, we're reflecting more of it away. So glaciers are just a really tiny fraction of this, just because of where they're located. They're real solitary figures or features in the cryosphere world. But they have a really important role when it comes to speeding up global warming. So as they melt, if they melt, they're going to decrease the albedo. Albedo is just the reflectance. So we're increasing the amount of radiation that we're bringing in because we're not reflecting it away. Also, glacial ice traps a lot of gas molecules and gas pockets. So that can release CO2 and methane, CH4. And as you can imagine, CO2 and methane, they're not going to be good for they're not going to be good for reflecting or keeping energy away. So that's going to be a positive forcing where it's going to increase the amount of insolation, the solar radiation that we're going to keep in. So we keep it a really close eye on glaciers just because they're usually a really good signal of when warming is going to happen and how fast it's happening on Earth's surface. So just to keep in mind, this is Shepherd Glacier. This is in Glacier National Park. This is from 1913. It's almost 100 years later, almost completely gone. So if you have plans on seeing glaciers in Glacier National Park, I would do so like in the next 3 years. Otherwise, you're not going to see it. Okay, so conversely, if we have warming conditions, that brings more precipitation. Remember, if we have warmer ocean waters, that promotes more water vapor coming up into the atmosphere. If we have more water vapor in the atmosphere, we're going to rain stuff out as snow or rain or ice. So snow and ice is what's going to create glacier growth. So as the snow packs down on the glacier, it's going to continue to get packed and packed until it turns into glacial ice. So if we get more precipitation, if we have a little more warming, we're going to grow those glaciers. So then we're back to growing the glacier, increasing the albedo, increasing the reflectance. So these things kind of roll in cycles. So what do we see today in the cryosphere? So before 2002, we thought the Antarctic was growing ice. Since then, and since we started collecting lots and lots of data, both the Antarctic and Greenland ice sheets have really steadily lost mass, and that in certain places that's accelerating. So to the left, that's Antarctica. That's accelerating pretty rapidly. Greenland, we have even more mass changing per year, 281 gigatons versus 146. So that's pretty significant. Okay. So obviously the sun is going to play a role here too. If we increase the solar radiation, we're going to increase the solar energy that we get on Earth. And that can happen a number of ways based on the sun's activity. The sun is pretty stable overall, but it does have periods of instability. So we can get things like sunspots. So during the Middle Ages, from about 1000 to 1400, we had this medieval warming period, as it's known. So there was a lot more crops available, a lot warmer period overall on planet Earth. And we can see this in historical reports. We can see this in the growth of the population. And there were a lot less issues related to colder weather during this period. Now we come to 1400, we're getting what's known as the Little Ice Age. Those sunspots are just going to go away. These tend to happen on different time scales than the Earth. But if we decrease the solar activity, we're going to decrease the solar energy that we're retaining and keeping on Earth. So this period is known as the Little Ice Age just because it was a lot colder during that time overall on average. There were a lot of problems with crop growth during this time. This is a really interesting period of history to study because the Little Ice Age made a very large impact on a lot of the civilizations on Earth at that time. So it's really interesting to study. We also have the atmosphere itself. What is the atmosphere made of? So as we know, the most abundant thing in our atmosphere is nitrogen, then it's oxygen, and then we have a bunch of other noble gases like argon, neon, helium. Helium is not a noble gas, but krypton and xenon definitely are. Wait a second, helium is a noble gas. Hydrogen is not a noble gas, excuse me. You can tell these sets of slides were made by a geochemist. So we have our permanent gases, the gases that make up the most of it, as nitrogen and oxygen. They stay constant. They're usually at those same proportions for most of Earth's history. They don't have much of an effect on climate. Nitrogen doesn't really affect it. The amount of oxygen has more of an effect on biodiversity than it does on the climate overall. And then we have these variable gases that can change drastically. So we have water vapor, carbon dioxide, methane, nitrous oxide, and all of these gases that can change with different geological events, different climate conditions, and they're going to really play important roles in how the atmosphere works and changes. Not only do we have gases, but we also have what's known as aerosols or particulates that we saw in that model at the beginning of the class. So volcanic ash is a huge one. We can also get smog and pollutants. Those are anthropogenic. They're induced by humans. So if we increase the amount of particles in the atmosphere, we're creating these like tiny little surfaces that can reflect solar radiation. So these vary with time, and obviously they're dependent on sources to create those pollutants in that volcanic ash. So those are more tied to eruptions and human activity. But these are going to end up cooling the Earth down just by how much they end up reflecting. Okay, so what do you guys think the primary gases emitted by volcanoes are? If you had to guess. Carbon dioxide and water vapor, right? Whenever we were talking about volcanoes, we were talking about volatiles, and the two biggest volatiles in volcanic material is CO2 and H2O. Not really what you imagine when you think of the word volatile, but they cause enough instability in magma to create violent eruptions, to build up. They're very highly active whenever they're induced with heat. So these are going to be the biggest gases erupted out of volcanoes. So let's say we have a huge explosive eruption, like the Siberian Traps, where we have an igneous province the size of Pennsylvania. Are we going to have a cooling effect on the global temperature or a warming effect? Yes. Cooling, very good. If we erupt enough material, don't forget, we're not just erupting gases and water vapor, we're erupting ash. And ash is going to be the critical factor here. If we have more eruptions, we're going to cool down the Earth overall. So, and we can see that in our historical record. This is just from 100 years of data. Each of those dashed lines, that's a volcanic eruption, and you can see immediately following that eruption, there was a period of cooling in the Earth that brought the overall temperature down by a couple tenths of a degree Celsius. So that's pretty significant that we see that in volcanoes. But keep an eye on this graph too. Where is the overall trend going? It's going up. So if our volcanic eruptions aren't cooling the Earth down enough, what's keeping the Earth warm? Okay, so how do we know climate is changing? Well, we have a bunch of indicators that we can look at. So obviously we have anomalous temperature data that we've collected for a long period of time. So starting in 1880, we have a really good temperature range. Bare bones average temperature was established in that range from 1951 to 1980. And anything deviating significantly from that line is going to give us what's known as an anomaly, or significant difference in a measured temperature from a reference. So if we look at from 1950 to 1980, it's around that 0 line. We had it much colder beforehand. Since then, it's been nothing but above that line. Also, keep in mind some of these like dips and changes in it. So right around in between 1900 and 1920, we have this huge dip. What do you think is causing that? I think 1918, two significant events. One, you're kind of living through right now. Yeah, the Spanish flu. It was a huge, huge pandemic in 1918. You had a massive decrease in the human population on the Earth. If you have less people doing less things and using less energy, you're probably going to have an overall decrease in the temperature. Not only that, but during the same time, World War I was being fought, one of the bloodiest wars in human history. So that's going to decrease the human population as well. Even though that war had a lot of industry behind it, there was a significant drop in the population, that less people were using less energy. So that's why we see that's one indicator that we can see a dip in that temperature. Also, we see a dip around the 40s. What was going on in the 40s? WW2, the sequel, that's right. Significant decrease in the population. So even though that one was even more industrialized, you see a lot less effect on the heat there. So another indicator that we have is change in sea level. Sea levels change constantly, and as you can imagine, As we discussed when we were talking about coastal hazards, we were talking about flooding, as we're melting glaciers, all of that water ends up in the oceans eventually. So that bathtub is going to basically start to fill up until it gets to the point that it overflows, right? So as sea level rises, that's going to be an indicator of melting of ice caps, melting of ice, and we have to figure out where that water is coming from, right? So we have ground temperature data for going back 143 years, long period of time. From the 90s, we have much better quality data from satellite imagery. If we can measure sea level from an exact orbit in space, we're going to limit the number of variables that go into collecting ground temperature data. So if you have a bunch of people around the world collecting sea level data, it's really hard to sift through that. So if you have a bunch of satellites in orbit in the same constant distance from the Earth's surface, it's going to be a lot easier. So right now we're at around 3.3 millimeters per year in rise, and that doesn't sound like much, but that's the entire ocean. All the water in the oceans on Earth rising at around, on average, 3.3 millimeters per year. That'll be pretty devastating if you give it enough time. And obviously we have measures of carbon dioxide levels. So there's a observatory in Mauna Kea in Hawaii. They started collecting this data in 1960. So this is coming up on 70 years now. Not 70 years. It'll be 70 years soon, but 60 years now. So we have a lot of data in this specific observatory. And as you can see, there is this crosshatched. All of those points are just significant little data points calculated every day for daily measurements of CO2 from this one specific observatory. It's the best area in the world to collect carbon dioxide data just because Hawaii doesn't have a huge human population. So the direct CO2 emissions from cars and industry is going to be lower. So you're going to get more atmospheric CO2 from the overall planet because you're out in the center of the ocean. You're away from major industrial centers. You're not getting a lot of skewedness in your data. So that's why we have it out there in the middle of the Pacific. But as you can see, it has a pretty not so subtle direction. So each of these little crosshatches, that's the annual variability that we see. So as you can imagine, CO2 is going to change based on a lot of things throughout the year. So if you think about certain areas, maybe in the winter like we have now, you're probably using more electricity to heat your home, heat your business, stuff like that. So CO2 emissions may go up. As you're coming out of the colder months, CO2 emissions may go down. So there's a lot of things that go into play here, but it always has that general trend. Okay, so we have average surface temperatures increasing, a rising sea level, rising carbon dioxide levels. And so is the climate changing though? And this is a really hard question to answer because we have so many different moving parts here. Remember, correlation does not equal causation. So just because all of those things happen to line up doesn't necessarily mean that the climate is changing. But we have ways of figuring that out. The best example I can give of correlation not equaling causation, there's a website you can go to called Spurious Correlations. If you take data from the number of majors at FSU, the number of computer science majors at FSU by year, and the data for the number of people that have been strangled by their bed sheets by year, that data correlates perfectly. It is a direct line. Are those two related in any way? Of course not. There's no way those two data sets can be related. But the data works so well and it looks so good on a graph that you would think, oh my God, if we have more majors of computer science at FSU, more people are going to die by strangulation. That's not how science works. So whenever we see correlation, it's a good thing to start asking questions about it, but we need more studies to understand it and understand the actual relationships behind it. So climate is actually always changing. From the beginning of the Earth's history, we've always had changes in the climate. As you can imagine, think of how crazy and violent Earth's history has been for 4.6 billion years, since the beginning, where we've had so many asteroid impacts, large meteors taking out the dinosaurs, huge volcanic eruptions that wipe out species. Of course, we're going to have different changes in climate. And these happen on long-term fluctuations. We mentioned plate tectonics. Remember, plate tectonics are moving really, really slow, but over long-term periods of time, they're changing the Earth constantly. So based on where these continents are, where land is on the surface of the Earth, we're going to change the climate. So if we're all smashed together, we're going to have a different climate than when all the continents are spread apart. Same thing if we have variations in Earth's orbit. Earth is orbiting around the sun, so we're going to have our impacts from the sun, as well as we're going to have variations in how we're rotating and our axial tilt. So that's going to have an effect as well. So keep an eye on this graph. This is average oxygen throughout the Phanerozoic. So we have Neogene, where we are now on the left. We're at 0 million years ago, so today, versus all the way back to the Cambrian period on the right, 542 million years ago. So in this period of time up here, anything above 0 is going to be hot. We have more oxygen isotopes, oxygen 18. Anything below here, we're going to be cold. This is where we're going to have our glacial periods, where we're going to call what we call snowball Earth, where we have ice sheets everywhere, more ice, more snow, more colder temperatures. So keep an eye on where we are currently. So what does a warmer climate look like? So during the Mesozoic and the Ordovician and Silurian, you're going to have more seafloor spreading, so bigger oceans. You're going to have more volcanism, and as you get more volcanism, you get more carbon dioxide in the atmosphere. So remember, CO2 is one of those volatiles that's in eruptions, one of the biggest ones. You have shallow oceans, you have less dense ocean crust, so because of that, you have a lot more marine life that likes these warmer waters. As you can imagine, it's a lot harder to heat more volumes of water. So imagine filling a cooler with ice and how easy it is or boiling water on your stovetop. If you have less water in it, it's going to boil in a shorter amount of time. More water, it takes a lot longer, right? So if we have less water, if we have shallower oceans, it's going to be easier to warm those up. So we don't have any glacial ice in these areas, maybe at really high mountain altitudes, maybe maybe a couple 100 meters above the tree line, but we're not going to see them everywhere. So because of this, what kind of life is going to benefit from this kind of environment? Cold-blooded life. So we have the dinosaurs. This is their reign. They're the kings of the earth at the moment. And since they're cold-blooded, they're adapted to a warmer climate. Because there's so much oxygen in this area, that's why they're able to grow so large too. More oxygen enables them to grow much, much larger. So they're gonna survive very well in this situation. Keep in mind, during the Ordovician and Silurian, sea levels were 200 meters higher than where they are today. 200 meters. That's why you can find oceanic fossils all the way inland in America, which is crazy to think about. Okay, so what does a cooler climate look like? So if we're locking up water in glacial ice and ice sheets, that means that water isn't flowing to the ocean. So we're going to decrease the sea level. If we decrease the sea level, we're going to have a lot more incising. We're going to have a lot of really cool geomorphic features that are created. Those deep sea canyons are going to form. We'll have less seafloor spreading. This is where we have Pangea. All the continents are smashed together into one supercontinent, and that landmass is very, very cold. So we call this snowball Earth. That specific one, the snowball Earth model, was from 2.4 billion years ago. So we don't have, this is long before dinosaurs and long before us. The Earth is only half its current age. So we have all this is just covered in ice. So if we have more ice, we have more reflectivity, we have more albedo. So if we're reflecting more, we're going to create cooler temperatures. We have less solar energy. We're going to make a lot more ice because of that. So let's make sure that we can read this graph properly. In terms of geologic time in long-term periods, is the current climate relatively warm or cool? Not you, Ed. Yeah. Cool. That's exactly right. Remember, we're over here on the left. We're much lower on that scale. We're below our zero relative reference point. So we're technically right now, we're in a much cooler period than we've had in past times. So are we currently in an ice age is a good question as well. So during the Pleistocene, around 21,000 years ago, this is what the Earth looked like, specifically North America. So this is where we have what's known as the last glacial maximum. You can see all those ice sheets going all the way further down south, covering a lot of Pennsylvania, a lot of the Midwest states where the Great Lakes are, so Wisconsin, Michigan, that area, all the way covering down. All of Canada is covered in ice. Most of the Pacific Northwest is covered in ice as well, even down into like around Idaho. So we're covered in ice in these areas. So we're at least cold enough to have ice sheets on the surface of the Earth. Greenland's elevation is not very high. So remember, whenever we have those warmer periods in Earth's total history, we don't have ice sheets at low altitudes. We only get ice and glaciers up in those high mountain altitudes. So we're still in this glacial period where we're able to have glaciers. And we've had multiple ice ages over the past. So like we said, last glacial maximum extent at 21,000 years ago during the Pleistocene. Because of this, the global sea level was 100 meters lower, and this covered around 10 to 30% of the Earth's surface, which is a pretty huge area. You can see all those ice sheets coming off of Antarctica up into the Arctic. And we have these huge ice sheet systems, these four specific ones: the Cordilleran, the Laurentide in North America, the Scandinavian. All those ice sheets are going to carve out valleys and form those fjords that you see in Norway and Sweden. And of course, Siberia. It's still cold there today, but it used to be a lot colder and covered in tons and tons of ice. So we don't get ice ages frequently. We've only had roughly 5 in our entire history. So remember, we have the Hadean Eon, 4.6 billion years ago, up to 3.9. The Archean, starting to develop some life. And then we start to get cooler, right around the beginning of the Proterozoic. So we get a little cooler during that time. That's where we were at snowball Earth, around 2 billion years ago. Later in the Proterozoic, we get another ice age. That's where we have this huge die-off, this huge mass extinction event in all those like sea critters that you see on the ocean floor. As we move from the Proterozoic to the Paleozoic, we're going to continue through the Ordovician and Silurian, get another mass extinction event with the Permian Ice Age. Those things are used to warmer climates. You lower the temperature, you create large ice sheets, they're not going to handle it so well. And then as we continue through the Mesozoic and the Cenozoic, we're back into the Pleistocene Ice Age, starting around 2 million years ago. So keep in mind, this is a really far recurrence interval. And obviously we've calculated these in the past. I'm not going to ask you to do that again just because you've done it so many times. You should be good by now. But there's a lot of space in between there, like 600 million years in some cases. So it's a very huge gap in between them. So what is the reason for that? Plate tectonics. So where the land masses are on Earth is dramatically affecting how the climate is going to work. If we have all of these smashed together in Pangea, we're going to have a lot more capability for deeper oceans. If we have deeper oceans, we're going to have a lot colder currents, colder waters. As we're spreading out, we're going to change where those currents are going to end up going. So 85 million years ago, this is what the Earth looked like. You can see part of the general shapes here. So obviously up in North America, we have this great inland waterway, as it's known, right through the center of the continent. We've got some flooding in what's going to become the Andes Mountains. The Sahara, one of the driest places on Earth today, used to be covered in water. Crazy to think about. And then we still have all of these archipelagos in what's going to become the Mediterranean. You can see Spain a little bit. You kind of see where Saudi Arabia is going to start to coalesce. So these are going to end up smashing into each other to form those Mediterranean countries. Right off the coast of Madagascar, what is that? Who can tell me what that is? India. Very good. India is not even close to Asia yet. So it's already going to start coming in, and it's going to start its collision course with Asia pretty soon. So India used to be its own continent, and it's going to continue to drive into Asia. So, yeah.
I was just going to ask, like, on India, Asia, did geologists know like how big those mountains that are going to be?
So that's an interesting question. So whenever we talk about plate tectonics, there's this term that we use to describe these really stable pieces of crust. They're called cratons. So Siberia, in this case, is a craton because the crust is super, super thick. It's really stable. It's not going to subduct underneath anything. At the same time, over in North America, we have Laurentia, the Laurentide craton, also really thick, also super stable, not going to subduct under anything. So we think because of how much buildup has happened with the collision of India into Asia, Tibet is, as you know, it's a really high altitude, really cold there. It's a plateau, very flat, but very, very thick in terms of its crust. So we think that Tibet is actually going to start to form into a new craton. And basically, Tibet is going to be the most persistent, one of the most persistent geologic places on Earth. It may surpass like some of the past cratons because it's so young, it's so thick, and it's going to persist for a long period of time. It's not going to subduct anywhere. So that's a really interesting question. Most people think that's where Tibet is going to end up going. It's going to be a really, really stable continental craton that'll affect the other continents of the world pretty soon in geologic terms. But yeah, great question. Okay, so the key thing with this image is we have South America and Australia is joined with Antarctica. So, and as we know today, they're much more separated. So if we have those joinings of these two huge land masses, well, three huge land masses, that's going to drastically affect ocean currents and where they end up going. So rather than flowing underneath Australia and underneath and around Cape of Magellan, or the Strait of Magellan, it's going to flow over Australia and up through the beginnings of the Atlantic. So it's going to really influence where these currents end up. So because of that, this is what it looks like if we're looking straight on from the South Pole. If we turn the Earth to the side. So we're going to flow around this huge landmass rather than right through it. So instead of getting all this polar water flowing past and flowing around, we may end up not circulating enough cold water at all. And this is what it looks like to, not yet today. We're at 21 million years. So now we're starting to get that separation. Australia is fully separated from Antarctica, opening up that waterway. South America is pretty close, so it's still a little shallow in that area, but you can still flow water right across it. We're starting to close off all of those inland seas where the Mediterranean is. You can see the beginnings of the Caspian Sea, the Black Sea, the Ural Sea are all in there. And you can see a couple of seas near the Ural Mountains up to the north in Russia. Really interesting. So now that we've completely separated, we're going to be able to get those cold waters everywhere. We're going to flow those cold waters past South America, past Antarctica, and up the coastlines of South America, North America, Africa, everywhere. So right there is the Drake Passage, right in between South America and Antarctica. We're going to get cold and dense waters from the Antarctic, which is known as, denoted as AABW, Antarctic bottom water, because it's very cold, it's very deep. So we're getting all of this new ocean circulation into new places. So same time that's happening, Europe is separating from North America. So we're getting a new waterway from the other pole, the North Pole, getting all that Arctic water, not Antarctic water. So this is where we have the NADW, the North Atlantic Deep Water Zone. So we're pulling all of that down from higher latitudes to lower latitudes, and we're going to start to circulate new temperatures of water. Eventually, we're going to get the Gulf Stream going on, bringing up warm water up from the equator past North America. We're going to circulate in these colder areas because it's warmer water. Remember, we're going to increase the precipitation, and because we're in a cooler glacial period, we're going to increase the amount of glacial ice. So this is why we're getting that Pleistocene Ice Age, glacial maximum, huge ice sheets everywhere, is because we're increasing the precipitation by allowing warmer water to circulate into colder waters and increasing the amount of snowfall and snowpack on that glacial ice. Something else that we can get influencing these climates is Milankovitch cycles. So Milutin Milankovitch, he was a Serbian astronomer and geophysicist. He studied the orbits of the Earth, orbits of astral bodies, and the rotation of the Earth. So he noticed that in certain time periods, at certain time frames, there were changes in the Earth's eccentricity, which is its orbit around the sun, its obliquity, which is the rotational axis this way, and changes in its precession, which is, let me think, we'll get to, it's easier to describe them in pictures. Okay, so let's start with eccentricity. This is our normal orbit around the sun. We are not in a perfect circle orbit around the sun, so all of those dioramas you made in preschool were wrong. We're in an ellipse, more of an elliptical shape. And based on our distance to other gravitational forces, we can be pulled into longer and longer orbits. So as you can imagine, if we're increasing that ellipsis that we have in orbit, we're increasing our distance to the sun at certain points in our orbit, and changing and getting closer to the sun at other parts. So this happens around a time period of 100,000 years. Relatively young for geologic time, but still pretty long for what we perceive as humans. So low eccentricity, we're gonna have closer to a circle shape. High eccentricity, we're getting into an oval. Obliquity is the angle of tilt on its axis. And obviously we're gonna vary very little in this. We've always had this orbital tilt, but we have a tilt that ranges between 22.5 to 24.5 degrees from the regular orbital plane. So today we're around 23.44 degrees. And this happens at about half the time that those changes in eccentricity happen. So a lot more frequent than eccentricity. So keep in mind, as we mentioned, if we change that tilt, we're going to change the angle at which we're receiving that solar radiation. So certain areas are going to get more sustained solar radiation. Some areas are going to get more reflectance based on the angle of that incoming radiation. And then precession is the wobble. It's how our axis changes in its rotation. So the angle will stay fixed, but as it rotates, it's going to change its orientation. And this happens about half the time of changes in obliquity. So this is around 26,000 years. So it works kind of like a gyroscope, just in a weird wobbling shape. So if we change the wobble that we get, we're changing the amount of incoming radiation and duration of that radiation that we get on certain sides of the Earth's surface. So that's going to affect our climate as well. So this is if we graph this up, here is our, remember this is looking at it in terms of waves. So we have low frequency, low amplitude with the eccentricity, a more high frequency, high amplitude with tilt, and with precession, we're getting a lot more frequency, a little less amplitude, but a lot more frequency. So this is going to, excuse me, let me get some water. Mouth is drying out, talking too much. All right. So this is a net effect, meaning all of these are going to add up. So if we have periods of high eccentricity, high tilt, and high precession, as you can see on the bottom, we're going to increase that overall effect. If we have, we're creating all these different summations and equations to subtract and add these different periods of eccentricity, tilt, and precession during different time periods. So if the combined effect is low, we're going to get less insolation. So we're going to get more ice. So each of those blue blocks, those are periods where we're going to get ice advance. We're going to get maybe ice ages. We're going to get a lot more ice sheets, a lot more glaciers. So we're going to increase the amount of ice on Earth as a whole. So we can see this matches most of these cycles in Earth's tilt, axis, and orbit. Okay, so if we look at today, what do we have more of? Do we have more insolation or less insolation? Yeah, more? Are you sure?
Oh, wait, sorry.
Yeah, we're less. We're over here. Remember, so keep in mind when you're reading these graphs, some of them are backwards, just because they're looking at extensions of time into the past. So the youngest, we're over on the left rather than what you would expect. We're over on the right. So we're at less insolation today than we are in the past. So keep in mind, within the Pleistocene age, we have these glacial periods where we're significantly colder. So this graph is from 2 million years to today. That's the beginning of the Pleistocene. But at the same time, we've had all these periods of significantly colder. So we're having temperature in this direction, time in this direction. So we have all these things to the left of our relative average. We're a lot colder. We have everything locked up in ice. We have a lower global sea level, especially around 10,000 years ago. We had a much lower sea level, 120 feet. At the same time that this is happening, we have these interglacial periods where things get significantly warmer. We're getting a shrinking in glacial ice. It's still going to be there, but they're smaller overall. As we're melting, we get that glacial meltwater. It's gonna go over the land and go into the sea. As we add more water to the ocean, we're gonna rise those sea levels up to about 8 meters higher than today. That was around 120,000 years ago, right before the Wisconsinian period. As you can imagine, Wisconsinian, Illinoisan, they're named after those ice sheets that were in the Midwest. So, are we in a glacial or an interglacial period right now? Keep in mind where we are on the graph. We're not at the bottom, we're at the top. Shout it out. Looks like interglacial, right? That's correct. You're currently in an interglacial period. So we are going to be warmer than what's normally perceived during the entire Pleistocene. Now, keep in mind, humans have only been on Earth for about 1.8 million years. So we have a very small reference point of what the Pleistocene actually is. So what does a typical interglacial cycle look like? So ours started around 12,000 years ago. We've got less than 30% ice cover. At the height of the last glacial maximum, we had 30% ice cover over the entire Earth. Now we're at 10%, and that's slowly and steadily decreasing. So obviously we have much warmer temperatures. So June of 2020 was the 44th consecutive June above the 20th century average. And 2020 and 2016 were tied for the hottest year on record ever since we started recording our global average temperature. And obviously we're getting increasing levels of CO2. Now, keep in mind, during natural systems, we're also going to get an increase of CO2 as well. As we're melting ice caps, melting permafrost, all those gases that are stuck and locked in that glacial ice as gas pockets, they're going to get released. And that's what we see in glacial and interglacial periods. So this is CO2 in parts per million. It's just a measurement of how much molecules of CO2 are in a certain measured amount of space. So during our glacial periods, all that ice is locking up that CO2 in those air pockets. We get more snowpack. That's as the snow falls, it traps those air pockets and it compresses into gas bubbles. So it's locking that up. As we're melting, we're releasing all that trapped CO2 into the atmosphere. So glacial periods, we've got lower. Interglacial periods, we've got a lot higher. So look at where we are over here on the right. We've got very, very high levels of atmospheric CO2. Okay, so in a natural system, what are the max and min values? This is just making sure we can read a graph. So I'll go back to this one since it's a bit bigger. So what are the maximum and minimum values of CO2? Yeah, Adam. I am more than inclined to agree with you. So yeah, around 295. It's hard to see. That's a tricky one because there's a line that extends up there. So you guys probably wouldn't have been able to see that. But we're really, really low on that end, around 180. So yeah, this is a pretty big range overall. Remember, this is parts per million. So multiply each of those numbers by 1 million. That's how much atmospheric CO2 we have. Okay, so this isn't the entire Pleistocene age, but this is the past Pleistocene ice age. So how warm are we by comparison? So the last interglacial period that we had was, when is that? 1300, so maybe maybe around 80,000 years ago, we had our last interglacial period. And during that time, during that interglacial period, this is where we have the separation of a lot of our human cultures. So remember, humans, as they evolved in Africa, they spread out over these massive land bridges that connected these continents. Some of those made it all the way through Siberia, over the Bering Sea land bridge, which was just this ice bridge that connected Siberia to North America. Then they spread down through North America and South America. At the Imean last interglacial period, we get that warming. So we're melting that ice bridge over the Bering Sea, and now we're separating those cultures. So it's not until the Vikings end up in Newfoundland that we get that interaction between those two peoples again, hundreds of thousands of years later, which is crazy to think about. I think that's really cool to think about. But so there we are approaching that zero value, and there is the Imean last interglacial period. So very, very warm up there. So keep in mind, 120,000 years ago, we are 8 meters higher in our sea level than we are today. Over the last 150,000 years, much shorter time scale here. We're fast approaching that interglacial period. So we're rapidly approaching this warming. As you can see, over the past less than 20,000 years, we did all of this rapid warming. Okay, now let's break it down into an even smaller time scale. The Holocene, last 18,000 years, where humans have had the most interaction. Whereas the maximum, the Holocene, that was around between 4,000 and 5,000 years ago. You can see the little ice age happening around the year 1400. So we're getting back down below that change in temperature. So we're still not at our full maximum yet. Now, let's break it down to the last 1,000 years, where humans are growing in their population, they're becoming more advanced. We have that medieval warm period where crops were able to be grown in more places. We have growing populations because of that, more exploration, more discovery. And then we have our little ice age where those temperatures dip down below our normal back in 1400. And here we are past 1850. Here we are rising quite rapidly. Compared to the rest of these, look at that medieval warm period, the shape of that warming, and look at our warming period starting around 1850. So keep that in mind. Now we have the last 140 years. And the last 140 years, that's industrialization. That's the Industrial Revolution. Prior to that, even though human societies had been highly developed, we weren't developed on an industrial scale. We didn't have machinery to build things. All economies were really based on craftsmen and everyone making things one at a time. Once we get to 1860, we get machine parts where we can standardize and make several of the same thing in rapid succession. So this is where we're growing in our industrialization, in our economy. So same thing as we saw in that temperature graph. What do we have in 1918? We have a dip in our global temperature. We have that Spanish flu, another dip during the 40s. And we've been continuing to rise ever since. And keep in mind, between 1950 and 1980, we're still pretty stable at that stage. Really stable. Okay. So we get to the final question of, is global warming really a thing? So the Earth has definitely been colder than it is today. That is for sure. But it also has been warmer than it is today. And we're also in an interglacial period where we have relatively warmer areas where we have less ice sheets. And during interglacials throughout geologic history, we have rising carbon dioxide levels, rising sea levels, and global temperatures. So is the Earth just really warming because we're in an interglacial period, or are we having an effect on it? Tune in next time in Geology 105 to find out the answer to that. So that's the first half of this. We'll go over the second half in how we look into the past of climate change and to see the natural climate changes that have happened on the Earth's surface versus what's happening today. Compare the two, and hopefully you'll be able to see for yourself the answer to this question. So if you have any more further questions about this, if you want to talk about climate change, or if you want to talk about the exam coming up or need help with any of that material, I have office hours today, 4 to 5. I'll also be in my office most of the day. So if you email me, make an appointment, I'll most likely be there. So have a great Wednesday, everybody.
Thank you.
Oh, also keep in mind, your exam 2 is covering tsunamis, volcanoes, and rivers and flooding. No coastal hazards. Alrighty.